Welcome to Podkey Slopcast, where grand unification and self-driving hype both get pressure tested. Some ideas sound inevitable because they're elegant. Others sound inevitable because investors keep repeating them. This batch has both kinds, the theory of everything and the robo-taxi future. Physics has real wins on unification. Newton tied falling apples to orbiting planets with one law of gravity. Maxwell merged electricity and magnetism, and in the process exposed light as part of that same framework. Einstein then fused space and time into space-time and connected gravity to geometry and acceleration. So when physicists talk about a theory of everything, it's not just metaphysical branding. There's a track record here. The electroweak theory already combined electromagnetism and the weak force in the 1960s, and grand unified theories try to pull in the strong force before gravity enters the picture. The catch is that each step gets dramatically harder. Don Lincoln's estimate of maybe 50 to 100 years for a full theory is not a casual delay. The relevant energy scale is around 10 to the 15 GeV, far beyond what today's accelerators can reach. Historical progress has sped up in calendar time, but the experimental hill has become almost absurdly steep. So the optimistic case is that theory, cosmology, and indirect measurements keep narrowing the options. The skeptical case is that without direct access to those energies, elegance alone can carry too much weight. Both are fair. The stronger claim is simply that unification is a successful method in physics, not that the last step is close. The Higgs story is a good example of where physics has solid footing. In the early universe, about a trillionth of a second after the Big Bang, the Higgs field switched on. That gives mass to the W and Z bosons while leaving the photon massless, which is why the weak force is short range and electromagnetism reaches across the cosmos. And the 2012 LHC result was not just a flashy particle bump. The particle found is consistent with the Higgs proposed in 1964, spin zero and decay channels into bottom quarks, W and Z bosons, and photons that match the theory well. But the Higgs exists is not the same as the Higgs sector is finished. Current data still leave room for extra Higgs-like states, including possibilities from supersymmetric extensions. So this is one of those cases where the central claim is strong, while the broader interpretation remains open. Part of why these discoveries are hard is raw volume. The LHC generates around 40 million proton-proton collisions every second. Hardware triggers slash that to roughly 100,000 events per second, then software cuts it again to about 1,000 worth saving. That filtering is not a side detail, it's the experiment. CMS and Atlas weigh about 14,000 and 7,000 tons respectively, and they push petabytes of data each year. Rare signals like the Higgs are found because the trigger and data pipeline are good enough to keep the unusual event without drowning in ordinary ones. That also matters for future claims. If somebody says a new fundamental particle is hiding in the data, the burden is not just statistical significance, it's whether the whole chain from detector response to trigger logic to reconstruction supports it. Antimatter is a nice place to separate cinematic imagery from engineering reality. Fermilab's old antiproton source could make about 10 to the 12 antiprotons in a 12-hour run. That sounds huge until you convert it. It's around 10 to the minus 13 grams, roughly a nanogram per year at that pace. NASA's estimate for a gram of antihydrogen is about $1.5 quadrillion, and each antiproton takes roughly 100,000 protons smashed into a target. So whenever antimatter gets discussed as a practical fuel in macroscopic quantities, current production numbers basically kill the idea. The deeper antimatter question is not production anyway. It's why matter won. Baryogenesis only needs a tiny excess, roughly 1 part in a billion, to survive the early annihilation era and make everything we see. But the standard model's observed CP violation in meson decays is way too small to explain that. That's why people look at leptogenesis and neutrinos, Fermilab experiments, including work tied to Don Lincoln's group, compare neutrino and antineutrino oscillation rates. If those differ enough, that could provide the asymmetry mechanism. The important word is could. There's a serious target here, but no confirmed answer yet. Dark matter and dark energy get lumped together in public discussion, but they are different problems with different evidence. Dark matter has unusually strong observational support. The bullet cluster is the cleanest case. After a collision, the hot gas and the gravitational lensing mass are separated. That is hard to square with ordinary matter alone and fits a collisionless invisible mass component well. Then you get galaxies like Dragonfly 2 and 4, which seem to behave as if their dark matter halos were stripped away, and their remaining rotation looks more Newtonian. That is interesting because it supports dark matter as a thing galaxies can lose, not just a universal tweak to gravity applied everywhere in the same way. What has weakened is not the case for dark matter existing. It's confidence in specific candidates, especially WIMPs, decades of null results from direct detection, indirect gamma-ray searches, and colliders have widened the search massively. Dark energy is murkier. Cosmic acceleration is observed, and a cosmological constant is still the simplest bookkeeping device for it. But the theoretical crisis is brutal. The observed dark energy density is tiny, around 10 to the minus 99 grams per cubic centimeter, while naive quantum field theory estimates overshoot by about 10 to the 120. That is why people call it the worst prediction in physics. The likely lesson is not that the acceleration data are fake, it's that our vacuum energy reasoning is incomplete, and may be deeply so. Proposed fixes usually invoke a new field or symmetry that cancels almost everything and leaves a tiny residue, but no concrete model has cleared experiment. Quantum gravity is where scientific ambition and scientific discipline really collide. String theory offers a broad framework for combining gravity with quantum mechanics, but after about half a century it still lacks concrete low-energy predictions, and its huge landscape of vacua makes falsification difficult. Loop quantum gravity has had the opposite problem at times, more specific predictions, some of which were testable and failed. One early idea that high-frequency photons might travel slower than low-frequency ones was checked with gamma-ray bursts and not seen, which forced revisions. That's not an embarrassment for observation, it's exactly what observation is supposed to do. Foundational theories are not beyond experiment. Precision astrophysics, burst timing, and lensing can constrain them quickly. The missing piece is not whether nature can answer, it's whether our theories are asking answerable questions yet. On autonomy, the strongest pro-deployment argument is straightforward. The US sees roughly 40,000 traffic deaths a year, mostly tied to human error. If a machine can really reduce that, even by a modest margin, the social upside is enormous. There's also the productivity story. Andrew Miller argues autonomous vehicles could free huge amounts of driver attention and, in the more ambitious version, cut private ownership, reclaim parking for housing or green space, and make commuting less dead time. Those benefits are plausible in principle, but they depend on several things all being true at once. The systems have to be genuinely safer, cheap enough to scale, reliable in ugly edge cases, and available in enough places to replace ownership rather than just supplement it. That is where deployment arguments split. Waymo's multimodal stack of LiDAR, radar, and cameras buys redundancy and probably better robustness in difficult conditions, but raises cost and complexity. Tesla's camera-only approach is cheaper and more scalable if it works, but the criticism is that low-cost perception may be exactly where rare, dangerous failures hide. Neither trade-off can be judged by slogans. More sensors is not automatically better if the economics block scale, and software solves it is not automatically credible if weird edge cases remain stubborn. The real contest is safety per dollar at fleet scale. Then there's the definitional issue. Some deployed systems use remote human operators for ambiguous situations. If the human is only giving guidance, that's still different from continuous teleoperation, but it complicates claims of full autonomy. That matters for liability and public trust. Miller's proposal that manufacturers should bear 100% of fault when the autonomous system is in control is clean in one sense. It aligns incentives and gives the public a simple rule. But industry resistance is also understandable. Full liability could be existential for companies if the standard is broad and the legal environment is unpredictable. So the bottleneck is not only technical, it is legal and political. Public fear also responds more to strangeness than statistics. A Waymo hitting a chain and killing a cat, or a Tesla misreading a white trailer, feels uncanny in a way ordinary human error does not. Even if aggregate safety improves, weird failures can dominate perception and regulation. That means the forecast of major North American cities having large robo-taxi fleets by around 2035 is conceivable, especially in favorable jurisdictions, but not guaranteed. Expect uneven rollout first. Dense cities may get fleet economics. Low-density suburbs may need subsidies if robotaxis are supposed to replace ownership rather than remain a niche convenience. That's the through line on both physics and autonomy. Elegant stories are easy, constraints are hard. Thanks for listening to Podkey Slopcast. This episode was generated by Podkey. Create your own at podkey.fm.